Okay, so hello and welcome back. So now I have been actually basically the bench that you see over here. This bench is something that I have set up very recently, and my bench was way back over there somewhere in the kitchen actually, and now I have moved all of these things over here, and everything over here is kind of new, and I'm actually learning how to work with this with everything over here, because I mean you kind of, your hands will learn how to where everything is, and now everything, I mean everything has been positioned like 2-3 days ago, so I need to find my way through all of these things. But now, and there was a problem over here, and this multimeter over here was creating trouble for this oscilloscope. So I had to move everything to the multimeter over here, and then I had to move these things up here, and then these two power supplies I just put there over there for now. But now let's take a look at the signal that we had before. And the signal that we had before was a 15 kilohertz signal. So 15 kilohertz is the same thing as 15 into 10 raised to the power 15 into 10 raised to the power so if you want to create that sort of signal on your basically on your let's calculate this again. So if you want to create a 15 kilohertz signal on a digital oscilloscope, it's easy, right? Even on a signal generator, you can very easily set your signal to 15 kilohertz without any problems, meaning that this is 10, and then if I move this to basically 1.5, for example, somewhere over here, then I know that my signal is something about 14.3 or 15 kilohertz. So that way you can create it. But if you didn't have access to any of these things, and if you had just a knob without any graduations on it, and you wanted to set the signal over there to create it, you would simply connect the output of your signal generator, whatever it is that is generating the signal for you. You would connect it to the output of the oscilloscope, and on the oscilloscope you can see that now I'm going to the trigger actually. So you would connect it to channel 1 of your oscilloscope, for example, and then you have to make sure that your reference line is ground. Of course, not important right now. And then you would have to essentially set up your signal in such a way that your frequency becomes 15 kilohertz. And 15 kilohertz means that, so let's see what 15 kilohertz actually means. So 15 kilohertz is the same thing as 15 kilohertz is the same, if your frequency is 15 kilohertz, that means that you have 15,000 cycles per second, right? 15,000 cycles per second, that means that your period is the reciprocal of this in seconds, meaning that 1 over 15 into 10 raised to the power 3 basically seconds, which is now 1 over 15 is the same thing as 1/15. 1 over 15 is the same thing as 0.0666, and so on and so forth, right? So that's 0.06, for example, 7 into 10 raised to the power negative 3 seconds, which is 67,000th of a millisecond, right? So this is not easy for me to see on this scale on the oscilloscope, and so what I'm going to do is that I'm going to make this number larger. So I make it a for example a 6.7 for example, or since I have basically milliseconds and microseconds over here, I have to make this number a microsecond. So I essentially have to basically multiply this number so that would be basically 67 into 10 raised to the power negative 3 into 10 raised to the power negative 3 in seconds, which is 67 into 10 raised to the power negative 6 microseconds, right? I'm sorry, which is the same thing as basically 67, which is the same thing as 67 into 10 raised to the power negative 6 seconds, which is the same thing as 67 microseconds, right? So if you had a wave with a frequency of 15 kilohertz, your period would be 67 microseconds. So what I'm going to do is that I'm going to basically jumble this around, meaning that I don't really know where I am over here, and I want to make a 15 kilohertz signal over here. So I go to, and we said that the period is supposed to be 67 microseconds, right? 67 microseconds. I set this oscilloscope to, for example, 10 microseconds or 5 microseconds, and then 67 over here, it would be hard for me to show that. So 10 would be, for example, if each of these is 10, then I would need 1, 2, 3, 4, 5, 6 of these would be one complete cycle, right? And then I keep increasing the frequency until I get to 6. I get to basically about 7. I get to one complete cycle in 7 of these basically, right? So I increase the frequency here. Something like this, and still I keep changing the frequency. And basically now my wave has to have one complete cycle in 7 of these approximately. And 7 of these would be, if I move this around, so now what I have is essentially 1, 2, 3. So basically one complete cycle of this wave is from this point all the way up to this point. So 1, 2, 3, 4, 5, 6. So I have to essentially decrease the frequency a little bit and move this around. So I have 1, 2, 3, 4, 5, 6.4, for example. Now this frequency is about 15 kilohertz, give or take. And if I take a look at the signal on the counter, I will see that it is 14.8 kilohertz, which is exactly what I was looking for, right? So now this part is done, and now if I measure the amplitude over here, it tells me that the amplitude is, oh sorry, I keep going to the external trigger. The amplitude is basically, my volts per division is 5 volts, so I have 10 volts peak to peak. I have 10 volts peak to peak. So 10 volts peak to peak means that basically, based on the calculation that we did before, So V of PP would be basically 10 volts, and half of that would be V of P, which is essentially 5 volts. And V of RMS you can calculate from your V of P voltage. And the way that you do it is that essentially this is your wave. So this, from this point all the way up to this point, this is your V of PP, which is on the oscilloscope. We saw that basically V of PP was equal to 10 volts, and therefore V of P, which is half of that, would be equal to 5 volts. And we said that basically to get the RMS voltage, we have to divide this V of P by square root of 2. Okay, now or multiply by 1 over square root of 2. 1 over square root of 2 is something like 0.707, which is something like 70%, right? Or 71%. So if you calculate 71% of your V of P, it's going to be your RMS voltage, meaning that you can go over here and basically you have 5 volts V of P and multiply it by 0.71. That is 3.55 volts, which is supposed to be your RMS voltage, right? 3.55 volts. Now 3.55 volts, well, it is my RMS voltage because I can see over here that I have over here 10 volts peak to peak, 5 volts peak, and so 3.55 volts is naturally my RMS voltage, right? But now if I didn't have this oscilloscope and if I wanted to read this, I would use a voltmeter, right? A voltmeter, if I were to use a voltmeter, I could use, for example, this voltmeter over here. This is also usable. This is also a good voltmeter. It can do a whole lot of things. I mean, it's a small voltmeter, but it's essentially capable of doing many different types of things. So over here, if I connect the output of the signal generator to this, suppose that this is the output of my signal generator, right? And this is now the output. I connected these two alligator clips are connected to this BNC over here, right? Now, what happens is that, first of all, if I basically try to measure this voltage using an analog basically meter, what happens is that basically I can set up the analog meter to AC and set it to 10 volts, and if I connect it over here, let's see what happens. It's about, the meter is telling me that the voltage is about, on 10 volts, it's about, well, 3.5 volts, or give or take. It doesn't have any problems. Seems that it doesn't have any problems to show the voltage. Now this meter over here, if I go to volts AC, it has only 200 volts and 600 volts, so I set it to 200 volts. And this meter tells me that the voltage is 3.3 volts, not bad. Okay. Now this meter over here, this is not very good at voltages with high basically frequencies. For example, 15 kilohertz, I'm not really sure that it can even see anything. And when you measure the voltage, and this is on volts, 20 volts DC, 20 volts, I'm sorry, AC, you can see that I can't read anything over here, right? And on this meter, on the RMS meter, if I connect the voltage here, what happens is that, of course, this is AC, and you can see that I can read 3.4 volts over here, right? 3.4 volts. And of course I can make all kinds of changes to this voltage, meaning that I can keep changing the frequency. And let's even try this voltmeter over here as well. And if you try this voltmeter over here, volt AC, if you connect the negative lead over here and the volt over here, you can see that you can read 3.4 volts on this meter as well. But this meter cannot do that sort of thing. It's just not made for high frequency voltages, right? So what happens is that now I connect this over back to this meter, and I have 3.4 volts there. Of course, it seems that there is something wrong with this meter. No, sometimes the manual. 3.4 volts there, right? Okay. Now, what happens is that now, if I make some changes to the frequency of this voltage, then this meter will be able to actually read the voltage without any problems. Meaning that let's make the frequency a little bit. Let's, for example, make it, for example, 1 kilohertz, right? So if I make the frequency 1 kilohertz, so how do you make the frequency 1 kilohertz? So I connect this output over here. I connect this back to the oscilloscope, and this is my signal right here, right? You cannot see it, of course. This is my signal over here. So to make a 1 kilohertz, to make the frequency 1 kilohertz, your period has to be 1 millisecond, right? So I set this to 1 millisecond. And then the reason why I'm saying that the period has to be 1 millisecond, let me actually show you why that is. So I want to create essentially a wave, a sine wave with frequency, for example, 1 kilohertz. So 1 kilohertz is the same thing as 10 raised to the power 3 hertz, right? So that means that T would be equal to 1 over F, which is equal to 1 over 10 raised to the power 3 seconds, which is equal to 10 raised to the power negative 3 seconds, which is equal to 1 millisecond, right? So which means that essentially basically one complete cycle of this wave has to occur in 1 millisecond. So I change the time base of my scope to, for example, 1 millisecond, which means that then or half a millisecond, for example, which means that then each of these basically divisions each of these horizontal divisions is half a millisecond. And then if I create a wave from this generator basically if I create a wave from this generator whose one complete cycle occurs in two of these divisions would be 1 millisecond, and therefore the frequency would be 1 kilohertz, right? So let's see if we can do that. So now I need to I need to decrease the frequency a little bit, and as you can see, 0.2 times 10 is the same thing as, okay, so essentially you can see that one complete cycle of this wave is occurring in two of these exactly, give or take two of these. So that is 1 kilohertz. And if I connect this back here, you can see that the, I don't know why it is 2 kilohertz, but it is not 1 kilohertz but 2 kilohertz. So over here I have 0.5 milliseconds. So that means that one complete cycle has to occur in 1 millisecond. 1 millisecond would be something like this. So I have to so if I take, for example, if I read from this point, one complete cycle would be something like this. So if I so this is exactly, give or take, 1 millisecond. And as you can see, of course you cannot see exactly, but it's 1 kilohertz, right? So now what I'm going to do is that I'm going to connect this back to this meter, and you can see that I have the exact 3.38 volts that I had before, but now this meter will be able to see the voltage as well, because now we have decreased the frequency to 1 kilohertz, and it can read 1 kilohertz without any problems. And you can see that now it can read 3.392 volts, right? Now there is of course all kinds of different, basically AC. So essentially the wave that we had over here is not the only type of AC that we can generate. AC means that, so for example, if I connect this over here, and if I increase the amplitude a little bit and this frequency a little bit, so this is AC, right? And this is a sine wave. I'm sorry, you cannot see anything. So this is AC, this is AC, and this is a sine wave. Now I don't know what the frequency and everything is, but that doesn't matter. The point is that you can create a sine wave, you can create a square wave, you can also create a triangular wave, right? And so for example, if you have an RMS meter, something like this, it can read the, if you give it a triangular wave or give it a square wave or give it a sine wave, it can read that for you all the way up to I don't know, probably 50 or a couple of megahertz probably. I don't know exactly the frequency on this, but essentially, for example, then this kind of meter would not be able to measure that for you. So that's essentially what you need to. I mean, that's essentially what a RMS meter does for you. An RMS meter is essentially an oscilloscope, but it doesn't have the screen. It just shows you the numbers over here. But essentially, almost every logic circuit that you have in an oscilloscope, you have it inside this meter or this meter. For example, these two meters are essentially two pretty complicated meters. So that's basically that. So now we know basically how to do calculation on the time base of an oscilloscope, meaning that we know how to calculate basically essentially the period and the frequency of the wave, and we also know how to calculate the amplitude of the wave. We know basically V of peak to peak and V of peak, and also we know V of RMS. And using these concepts, now we can go and basically learn a couple more things about some components, for example, resistors or inductors in these AC circuits. So I'll see you in the next video with some more theory. Thank you.